Yes, I have two questions, one for Dr. K and one for Dr. Wells. First for Dr. K, just as a point of clarification, on your energy chart, you mentioned energy, but your units were power, and I wonder what the time factor was. And then for Dr. Wells, have you considered the role of propane in your mix of fuels? Excuse me, I'm Tom Bartley of Tom Bartley Ideas. I'm independent.
Okay, I apologize for any confusion. The usage of energy worldwide per year is currently about 15 terawatts. So that's why that's a power measurement. And about 85,000 terawatts equivalent of sunlight hits the terrestrial surface of the Earth.
Okay, to answer your question as best I can. Propane. I mean, there's no reason why you couldn't put propane or even butane in a internal combustion engine. Propane and butane are just a lot less abundant than methane, so they are much more expensive. You know, in the US, the propane market is very closely linked to fuel oil market because it's used for space heating. So, whereas natural gas or methane is not so closely linked, and propane is a natural gas liquid that is much less abundant than methane. So, if you're going to go for an industrial scale fuel system, you would tend to favour something which is very abundant and therefore likely to be cost effective and long term. But there's technically no reason why you couldn't use propane. No, none at all. Yes, you've got a high pressure liquid tank in the car instead of a high pressure gas tank.
Mike Ramsey with the Wall Street Journal. I wanted to ask, in terms of your model for oil demand and production, one of the things that I wonder about is as the production declines and the how you figure in the demand curve when
Right.
if prices go much higher, then you assume the consumption would drop because the 2.4% penetration of Prius sales would go to 10% or 15%. You know, I mean, how do you figure that out? And is this a problem that will solve itself? Is a longer way of asking. As prices escalate, we will use more natural gas and all these things because we have to.
Absolutely, but it's a problem that will solve itself. It'll just be disjointed. You know, the solutions won't arrive at the same time as the problem. I mean, there's a lag between the solution and the problem occurring. You know, if you read most of the peak oil literature, it talks about, you know, well, the oil price will just do this. Well, the oil price will not just do that. You know, the oil market has been punctuated by supply-demand crises for as long as it's been around, and usually there's a spike and then there's a demand response and then so on. So yes, you're absolutely right. I mean, solutions will come along, and they already exist, which will suddenly become economic to do. The issue will arise is that you have a price spike and a demand drop, and everyone gets comfortable again, and then you have another price spike. So, you know, the period when oil starts to become, how shall I say, when the incremental supply no longer meets incremental demand, which is roughly the situation we're going to be in for a while, is a very tricky period because you don't get a smooth price rise, you get a series of jerky responses. And I think that's the rather awkward market for both traders and consumers, because the price is going to be volatile and the solutions are going to be marginally economically effective and then not effective and then so on. So, you know, it's going to be a rather unpleasant period, I think, is my view. But it's not going to be linear, no, non-linear, distinctly.
Steve Ashley, Scientific American. I have a question for Dr. K about scalability of advanced biofuels. When I talk to the people in this field, they basically refer to batch processes in bioreactors where you have to maintain flows of nutrients and solar rays on some kind of substrate that holds the little guys, in place, and then you have to get the stuff out. Is this an engineering problem? Is it amenable to engineering? Can it be made on mass scale? And what's happening on that area? Because I haven't seen much change in many years.
So, look, I think that there certainly hasn't been much change, and I think prior to just the last 3 to 5 years, okay? But the reason for that, I think, is because there was essentially minimal investment in these organisms, right? I mean, if 1% of the R&D budget went to plant and microbial science, 1% of that, if you're lucky, might have gone to algae. So listen, there is a major engineering component in this. And I think in the same way that we talk about how there's going to be, you know, a patchwork of terrestrial biofuel crop solutions. So, you know, what's growing down in Florida will be different from the miscanthus in Illinois, will be different from rapid coppice forest and wood answers in the Pacific Northwest. So when it comes down to some of these microbial and or algae solutions, there absolutely have to be major advances in engineering. And I think that's why you're seeing a number of different biological start points. So there are people, you know, there are companies that basically don't want to deal with the photo part of a bioreactor, and so they're essentially, their starting point, their feedstock will be sucrose. And in that case, you're really looking then at standard fermentation technologies, just like the cellulosic guys are. And then it's a matter of how many big steel vats can you cram together somewhere. On the photobioreactor side, it is completely an open field for innovation. And that's absolutely where we have to get innovation. The paddle ponds that have been used for 50 years out here in the Imperial Valley. We have one of the best nutraceutical companies that grows spirulina, which is a cyanobacterial algae, which actually can be used to make fuel, but it's used as a nutritional supplement in that case. That 1950s technology, when you model that with a full life cycle assessment for fuel production, is a nightmare. So, you know, you can go and look at companies like Joule, who are based on the East Coast, who are coming up with thin film bioreactors, and they're actually putting papers into the peer-reviewed literature so that the scientific community can assess them properly, and there are encouraging moves on that. You know, there's, you know, people at Arizona State working on photobioreactors. You know, Sapphire has its own plan in New Mexico where I think it's about 10,000 acres of a new type of pond technology that I don't know what it is, but it sounds very exciting. So there is a huge engineering component for this to be able to work. It's not just the biology.
I'm Dennis Simonitis, Road and Track, for Dr. Wells. In one of the slides you showed, with the encouragement of ICE efficiency and CNG, you mentioned discouragement of corn ethanol, granted, and also discouragement of second-generation biofuels. By that, do you mean cellulosic?
Yes.
Okay.
Paul Williamson from Toyota Motors. Dr. Mandel, you talked about the volume of cellulosic material from plant on Earth. Toyota is currently making extensive use of cellulose to make bioplastics for our vehicles. And I wonder, between you and perhaps Dr. Wells, is there any, or Dr. K rather, is there any synergy between using plant cellulose for bioplastics and using some other part of the plant for biofuels, or are these uses in conflict?
Well, I think that I'm not very familiar with what parts of the biomass you use for the bioplastics. It may depend upon the type of biomass that you're talking about. So not all biomass is created equal. If you have woody biomass versus grassy biomass versus other sorts of waste from agricultural residues, you might want to think about how those different biomass streams look like and how you might want to tailor and optimize their use depending upon your ultimate applications. So just as different biofuels are better, or different sorts of biofuel conversion technologies are better suited to different feedstock streams, the production of different bioplastics and, you know, and the competition with those feedstock streams for the fuel versus the other sorts of materials should be taken into account. And, you know, I assume that economics will kind of play out there and determine what makes the most sense there.
I mean, just to add to that, yes, I think there's a number of real bioproduct opportunities, and certainly several of the people who are interested in algae are already moving quickly to look to see how algae oil can replace palm oil and soybean oil, for example, to make foams. So our algae center here in UC San Diego was approached by a surfboard company to see if we could produce a true green surfboard made from algae oil instead of soybean oil.
I think just to add to that, I think that one of the points is that when you look at this biofuels, it's not just a biofuels industry, it's a biofuels and bio-based products industry. So you need to look at the entire production stream to think about the economics and what makes sense so that you use the different biomass accordingly.
For my own personal curiosity, Peter, what do you think? We're watching the events unfold in Libya right now, and understanding the supply implications for oil. And looking into your crystal ball, what do you think the real risks are for similar type disruptions, given the same set of criteria that exist in places like Bahrain and Saudi Arabia, for further supply disruptions in the next few years? How about that?
Yeah, that's a question I really would like to duck. I'll duck it by giving a really short answer. I don't know.
Thought I would coax something out of you, but anyways, all right. Well, thank you all very much for your wonderful presentations and for all the good questions.